What's up, guys? It's me, Sir Ernest, and today we're going to discuss the physical pendulum. A physical pendulum is a rigid object that is free to swing under its own weight about a fixed horizontal axis of rotation. So we also call this the compound pendulum. So consider this rigid object that is free to swing about this axis. Here, our axis is our z-axis. So here we define several things. First, we define the position of the center of mass with respect to the axis of rotation r. And in vector notation, this is equal to L r hat, where L is the distance between the axis of rotation to the center of mass, and r hat would be the unit vector along the direction of r. We also define the gravitational force Fg, and this is equal to mg vector, or more specifically, this is equal to mg j hat. Therefore, the torque can now be calculated as the cross product between the position vector r with the gravitational force Fg. Applying the definition of cross product, this will now become negative mgl sine theta k hat, where m is the mass of your object, g is the gravitational acceleration, L is the distance between the axis of rotation to the center of mass, theta is the angular position of the r vector, and k hat would be the direction of your axis of rotation. On the other hand, Newton's second law for rotation is given by the net torque acting on the object is equal to the moment of inertia about the z-axis times the angular acceleration omega dot. In terms of theta, this will now be equal to I theta double dot. As you will notice, this is also in z direction. Therefore, if we're going to combine the two, this will now be rewritten as negative mgl sine theta equals I theta double dot, or theta double dot is equal to mgl over I sine theta. Now, if we assume small oscillations, sine theta can be approximated to be equal to theta. So therefore, the equation of motion for rotation is given by theta double dot equals mgl over I theta. So this is of the form of simple harmonic motion whose solution can be of the form theta equals theta naught sine omega t minus phi naught, where theta is the angular position as a function of time, theta naught is your initial amplitude in the angular direction, omega naught is the angular frequency, and theta naught is the phase difference. So therefore, the frequency of oscillation f naught is equal to omega naught over 2 pi, or simply 1 over 2 pi times the square root of mgl over I. And consequently, the period of rotation, which is just the reciprocal of the frequency, is now written as 2 pi times the square root of I over mgl. So if we recall, for a simple pendulum who's given by this figure, L is the length of the simple pendulum and m is the mass of the simple pendulum, the moment of inertia is just equal to ml squared. So applying this equation here, we can now have 2 pi times the square root of ml squared over mgl, which yields the expression 2 pi times the square root of L over g, which is indeed the period of a simple pendulum of length L. Now, for example, we have a thin rod of length A swinging as a physical pendulum about one of its ends. So let's recall that the period of oscillation of a physical pendulum is equal to 2 pi square root of I over mgl. Now recall that the moment of inertia for this uniform thin rod swinging about one of its ends is given by 1/3 ma squared. So therefore, the period of rotation is equal to 2 pi times the square root of 1/3 ma squared divided by mg times a over 2, where a over 2 is L, and that's the distance between the axis of rotation to the center of mass. And this can be rewritten as 2 pi times the square root of 2a over 3g. Now, this is now the period of rotation of a uniform thin rod swinging about one of its ends. And this is the same as a simple pendulum of length 2/3 a. So that's it. This is a short introduction to the concept of physical pendulum. I hope you learned something today. Thank you for watching, and I'll see you guys in the next video. Bye bye.